Okay, hello. Welcome to the last couple of sections about, sorry, there we go, about hypothesis testing with two population means. We're doing section 11.3 and 11.4 and then moving on to chapter 12 after that. Right now we'll talk about hypothesis testing with two means when we don't know the population standard deviations and we're dealing with dependent samples. And that would be the objective for section 11.4, not this one, so let's just skip that. So when we've got dependent samples, usually we're dealing with paired data of some sort. A good example of this would be pre-test, post-test type values. If I was doing something different in the classroom and I wanted to see if it made an impact, I could give you all a really quick quiz before class and then a really quick quiz at the end of class and see what the improvement was. And then this would be the test to see whether or not that improvement or change, we would hope it'd be an improvement, not a decrease in performance, so it would be significant. So usually what we're looking at here is the difference between the values. The value in population 2 and the value in population 1. And these differences should be paired. We do have the standard criteria for this type of test. All the possible samples have to, it needs to be a random sample. In this case, the samples have to be dependent instead of independent. Both standard deviations are unknown, and we have to have at least 30 pairs, or the population distribution of the differences has to be approximately normal. We're looking at the differences now, not the individual values. So I'm not looking at pre-test scores and post-test scores. I'm looking at the change between the pre-test and the post-test. And that's my new data, is that change. So since we're looking at a change and order is important when we're doing subtractions, it's important to have a standard way of deciding what's population 2 and population 1 so that we get the order the same each time. So the usual convention is to use whatever the post-treatment group is as population 2. So, this would be the post-test. It would be the after taking the diet pill. It would be whatever it is after the treatment. So you're subtracting off the before from the after. Right? So there it is. There's the after treatment, x2, minus before, whatever the initial value is. It's x1. So it's always the first value in the subtraction. So if there's some sort of improvement, we would expect to get a positive difference. If there's some sort of decrease, like a weight loss, we would expect a negative difference. So let's look at creating a null and alternative hypothesis for this. We've got a manufacturer claiming their diet pill helps a person lose more than 7 pounds in the first week. So we've got 15 volunteers who take the diet pill for 1 week. They measure their weights at the beginning and the end of the week. What are our null and alternative hypotheses? So take a minute, go ahead and write those out. Think about what population 1 is and population 2 is, and we'll move on. Right, so population 1 is that initial starting weight. Population 2 is the post-treatment value, so it's what it is after a week. We need to subtract each person's starting weight from each person's ending weight, so these values are paired. It matters which one we subtract from which one. If if it's working as intended, we would expect to see negative values because their finishing weight should be lower than their starting weight, right? The claim is they'll lose more than 7 pounds, so that means that difference is going to be less than -7, right? More than 7 pounds means they're going to be losing -8, -9, something like that, so it's going to be a technically smaller number. More larger absolute value, but smaller number, less than -7. So this is our research or alternative hypothesis that the average weight loss is less than -7 pounds. So the logical opposite is that it is greater than or equal to -7 pounds. And we can write those like so. There's our null hypothesis, h sub 0, is that the population mean of the differences, mu sub d, so that d tells us we're looking at the differences, is greater than or equal to -7 pounds. The research hypothesis, what we want to show is that it is less than -7 pounds. Okay. So, it's just restating the criteria. If the criteria, as restated here and as we went over a couple minutes ago, fit, and we can do this, random samples, dependent samples, at least 30 or an approximately normal underlying distribution. We're going to use the t-statistic, and this is now going to be based off of that difference. So we're going to take the mean difference of our paired samples. It's the mean of the paired differences for the sample data. We've got our presumed population mean difference, the standard deviation of those differences from our sample, and our number of pairs. So this is not the individual number of samples, it's the number of pairs we have. So one thing to note about this is that we can't have an odd number of individual data points. I can't take 28 pre-tests and 26 post-tests. Sorry, I shouldn't say odd number. I should say mismatched number. I have to have pairs for this. Our t-test, our degrees of freedom is that number of pairs minus 1. And as we've seen with other things, if we've got a left-tailed test, the null hypothesis will be less than or equal to. If we've got a right-tailed test, it will be greater than or equal to. If we've got a two-tailed test, we're dealing with an absolute value greater than something. Sorry, I misread this. This is the rejection criteria, not the how to tell. So if we're looking at something where we're looking for it to be less than a value, it's a left-tailed test. If we're looking for it to be greater than a value, it's a right-tailed test. And again, if we're looking for it to be equal to a value, it's going to be a two-tailed test. Okay, so let's look at an example. We have a driver's ed type course, defensive driving school. They're showing films of violent car crashes with the graphic pictures of injuries and want to scare the students into driving well. They've shown these for quite a while and believe they reduce the students' average speed on the highways. I've got a group of citizens who feel that these videos are very disturbing and are not convinced that they're effective on reducing highway speeds and improving highway safety. The group claims that the videos reduce the speed by less than 5 miles per hour on average. So they've installed electronic data recorders on the vehicles of 10 volunteers. So we've got we should have 10 pairs of data. They'll drive normally for 2 weeks, record their speeds, and then they watch the videos and then record the speeds for another 2 weeks. So we've got 10 pairs. Got kind of an average speed for 2 weeks before, average speed for 2 weeks after. We're looking at the difference. So we've got a table in the next slide of the data for this. We want to test the claim that the videos reduce the person's speed by less than 5 miles per hour on average to a 0.05 level of significance. Okay, so here are our 10 students. There's before speed, after speed, before speed, after speed, before speed, after speed. So decrease, decrease, increase, decrease, 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 decrease. Wow. You had a couple of people who drove pretty fast all the time. So the question is whether this decrease is, on average, less than 5 miles an hour. So what is our null and alternative hypothesis? Well, we're going to set population 2 as the after value. Again, as we discussed, you use population 1 for before, population 2 for after. We want to subtract the average speed before from the average speed after. We are looking for a negative value. They claim that it's going to be, the speed will be reduced by less than 5 miles per hour. Thus, the claim is that the The claim is that the paired differences is greater than -5. Sorry, it took me a minute to throw, the negative number and less than or greater than does kind of throw me too sometimes. So take a minute and think about where -5 is on a number line, and that if you're seeing something greater than -5, it's going to be, -4, -3, something like that. It's a smaller number in terms of absolute value, but it is a larger number. So -4 would be a smaller speed reduction than -5. So we'd write this as the mean difference is greater than -5. Greater than -5 still could be a negative number. It's just going to be, -4 point something, -3 point something. It might be a positive number, but it's greater than -5. So this would be our research hypothesis. The logical opposite is that the speed reduction is greater than or equal to -5. Sorry, less than or equal to -5. Apologize. It does pay to take a minute and think through the positive and negative, in which direction you're thinking about, and what greater and less than means in those terms. So we can state these hypotheses such. Null hypothesis is that the mean difference is less than or equal to -5. The research or alternative hypothesis is that the mean difference is greater than -5. Okay. So we've got paired differences, and we're dealing with the mean of that. We're going to assume an underlying normal distribution because we've got only 10 data points. So we're going to use student's t-distribution. The level of significance was given as 0.05. Let's collect our data. We've got the raw data, so we need to calculate the paired differences and then the mean and standard deviation for those differences. We can do this here. There's before and after. We can calculate the difference. Then we can take this and calculate the mean and standard deviation as such. negative 3.57 and standard deviation of 2.35293. Again, make sure that you are carrying, if you're doing this all by hand and not electronically, make sure you're keeping as many digits around as you can until the very end. Don't round early. You'll introduce error by doing that, and we've seen that several times throughout the semester so far. So just a reminder. We can put this into our formula here. There's our mean paired difference right there. This is our presumed difference from our hypotheses, so that should be a -5. It's our standard deviation there, and we had 10 pairs there, such. And that comes to approximately 1.922. I say approximately because we are going to be rounding at some point to report this. Right, we use -5 for the mean difference because that's our hypothesized difference from the statement of our null hypothesis. Okay, so next step is to draw a conclusion and interpret the data. So with the t-test, unless we're doing it electronically where it's going to give us a p-value that we can compare to our level of significance, we're going to need to compare it to a critical t-value to make a rejection region. So critical t-value, we need the degrees of freedom. We had 10 pairs -1, so 9 degrees of freedom. That gives us a critical value of 1.833. We're dealing with the right-tailed test because we're looking for something to be greater than. So we'll reject the null hypothesis if t is greater than or equal to 1.833. Since the test statistic is 1.922 and that's greater, we can reject the null hypothesis. So we can see this better graphically here. There's our critical t-value, 1.833. We're just a little bit past that, so we're in that rejection region. So there is enough evidence at the 95% confidence level or 5% level of significance to say that the videos don't impact the driver's highway speeds by more than 5 miles an hour. I phrased that backwards, but the impact is less than 5 miles per hour on average. Okay, so looking at this on a calculator, looking for now we're looking, as it says, a two-tailed test for dependent samples with the sigma unknown. Ooh, excuse me. So we've got a clinical psychologist who wants to test the claim that there's a significant difference in a person's adult weight if they're raised by their father instead of the mother. This doctor happens to know 5 sets of identical twin boys who were raised separately, one twin by each parent. And they were willing to participate in the study to help test the claim. Each twin was weighed and identified as having been raised by the mother or the father. Well, that seems like a rather far-fetched situation that there'd be 5 sets of identical twins separated and raised like that, but yeah, okay. So here's our data. We've got the twin raised by the father and the twin raised by the mother, 5 sets. We want to know if this supports the claim that the twin raised by the father will be... All right, we're just after a significant difference. We're not after lighter or heavier, just different. We're after the 0.01 level of significance. So, null and alternative hypotheses. First question is labeling population 1 and population 2. Now, these aren't these aren't pre-test, post-test type things, so it becomes a little more arbitrary. But we need to figure out which one is going to be which. So let's just call the twins raised by the fathers population 1 and the twins raised by the mother population 2. All right, so the doctor claims that there's a significant difference if the person is raised by the father instead of the mother. If there is a significant difference, then the mean difference is not 0. So symbolically, that would be the mean difference is not equal to 0. So that is our research or alternative hypothesis. The mathematical opposite is that there is no difference. Doesn't matter who raises the twin. The adult weight is going to be the same for the pair. So that's our null hypothesis. We can state this as the null hypothesis is the mean difference is 0. Research or alternative hypothesis is that the mean difference is not 0. Okay. So, determine which distribution to use. So, we're dealing with paired statistics, or a dependent sample. We've paired statistics, not paired statistics, paired samples, sample differences. We don't know the underlying population distribution standard deviations, so students' t-distribution is appropriate. We are hand-waving past the sample size of 30 or underlying normal distribution. Level of significance was given as 0.01. So let's look at our data. Here they're going to set this up and show you how to do it in the calculator. So we're going to, in the calculator, enter those values from that table into a couple of variables. Right, so you can put the population 1 values in L1, population 2 values in L3. Tell it that L2. Tell it that L3 is equal to L2 minus L1, and it will spit those out for you. So we've got our paired differences here. Excuse me. We can tell it to go to statistics test. We want to do a t-test. Tell it we're doing raw data. Claim is that it is not 0, so we need to enter 0 for the null claim. Tell it that we're looking list 3 for the data. Two-tailed test, we want to choose that not equal to 0. That should be our, our research hypothesis test that we're showing. If we tell it to calculate, it will spit out the t-value. The p-value associated with that will give us the mean and standard deviation. And because we gave it the raw data, it will spit out the number of sample points for us, and we don't need to tell it the degrees of freedom. It's got the data. You can see that. So, draw a conclusion. The p-value was approximately 0.7305, which is greater than 0.01, which is our significance level. P-value is greater than alpha, so we fail to reject the null hypothesis. So there's not sufficient evidence at the 0.01 level of significance to say that there's a significant difference between the weights of adult male identical twins raised separately. So there's not evidence to support the doctor's claim in this. Okay.